let's get a good start to chapter 10 here. You're going to have a little practice with this in lab. Those of you that were in lab this morning, you got your practice. But let's briefly talk. Chapter 10 is about chemical bonding. Okay? And chemical bonding makes use of valence electrons only. So whether we're going to make an ionic compound or a molecular compound, it's the valence electrons that participate to make bonds. Okay? The other electrons will be essentially filled subshells that are just fine the way they are. The valence electrons, though, are the ones that will be added to or removed or shared in order to make atoms more stable. So if I have a magnesium and a chlorine, I can make a Lewis electron dot structure by showing those valence electrons as dots. So how many dots should I draw on that magnesium? If I'm just drawing the valence electrons, how many valence electrons? You just count the S's and P's, 1 through 8. So let's draw 2 dots. And we're not going to be too particular about where we draw those dots. That's not going to be a big deal. How many dots should I draw on the chlorine? How many? Chlorine, 7. Let's do 1, 2, 3, 4, 5, 6, 7. Okay. If we were to quickly write this electron configuration, 1s2, 2s2, 2p6, 3s2. In this electron configuration, which ones are the valence electrons? It's these ones, right? N equals 3 is the valence shell. Okay? So 3s2, that's what we've drawn right here. Okay? We've drawn those 2 valence electrons. Okay? If chlorine is 1s2, 2s2, 2p6, 3s2, 3p5, which ones are the valence electrons there? 3s2 and 3p5. Okay? Those are the valence electrons that we've drawn. Okay? This magnesium atom, though, is not stable. What would that magnesium atom like to do in order to become more stable, in order to become more like a noble gas? It would like to lose those 2 valence electrons. It would like to give those away. What would the chlorine like to do? It would like to gain 1. Okay, so let's take one of these and give it to chlorine. Okay? So let's draw the chlorine first, right? Gain 1. We end up with a Cl, had 7 valence electrons. Now it's got 1 more. So what charge would that chlorine be now? Minus, because electrons are minus, and it gained an electron. That's a Cl minus. That is a stable chloride ion, because that's 3s2, 3p6 now. Okay, that's good. Would doing this make that magnesium stable? Not quite, because it gave away 1 of its electrons to chlorine. What do you suppose it's going to do with that other electron? It's not going to keep it. What do you suppose it would have to give it away to? It would have to give it away to another chlorine, right? Okay. So 1, 2, 3, 4, 5, 6, 7, like that. So that magnesium would now, after losing 2 electrons, it would now be just Mg with no valence electrons anymore. What charge would it have? 2 plus. Okay. We would have this other chlorine, now a Cl minus. For every magnesium, then, that I have, in order to become stable, I would need how many chlorines? 2. And we know that. What's the formula for magnesium chloride? MgCl2. That's the whole idea behind switching those charges around. Right? That we need a 1-to-2 ratio needed to transfer all of the electrons. The goal in making an ionic compound, this is ionic, right? How do you know if a compound is ionic? Metal and a nonmetal? Okay. The goal in making an ionic compound is taking the neutral atoms, transferring the electrons so that the atoms become stable ions. And we need the appropriate ratio that's based on how many electrons need to get transferred. Okay? If that magnesium has 2 electrons to give away, but each chlorine can only accept 1, that means for every magnesium we need 2 chlorines. Okay? So that's why the charge switches to become the ratio. Okay? It's however many we have to give away have to be accepted by an appropriate number like that. Okay? So what I really wanted to show you here, these are the ions that we formed. Okay? And ionic bonding is actually the attraction between those oppositely charged ions. So here, let's draw the magnesium. Right here. Let's draw a chlorine minus over here. Let's draw another chlorine minus over here. Those are attracted to each other because they have opposite charges. That one will be pulled that way, that one. Okay. They'll actually stick to each other, right? With a magnesium sort of in between chlorines like that. Okay? They'll stick to each other. That's ionic bonding. Okay? It's that attraction. So we had to transfer electrons What does it mean when I say that we transferred electrons? What would be another way of saying that? Gain and lose. Magnesium lost electrons while chlorine gained electrons. Okay? So the metals tend to give away their electrons. The nonmetals tend to accept the electrons in order to become stable. And that's just based on sort of position on the periodic table. Okay? What direction we have to go for it to be like a noble gas. Okay? So the ionic bond that then forms is because we formed oppositely charged ions that then attract. Okay? That's ionic bonding. Okay? I have a joke here. Yep. What does this mean? Taken, not shared. We're going to talk in a second about what sharing electrons does, but you can think of that. Okay? So an ionic compound alternating ions stacked together. Okay? This was just one particular grouping of ions, okay? But that's not all there is. We're going to have lots of magnesiums and lots of chlorines, and they're all going to get totally stacked up together, sort of alternating. Okay? So you're going to have a whole big group. I think I showed you a picture of that a while ago. But it's, in other words, not just this group. It's got a whole bunch of them. You can, draw a little picture. Sort of looks like that. And it just continues that way through the entire substance. Okay? But the reason it's that way is because there's no particular direction to that attraction. Okay? A positive ion will be attracted to a negative ion and in any direction. So you're pretty much going to have positive ions surrounded by negative ions, and those negative ions surrounded by positive ions. So that's why they sort of alternate and stack up that way. Okay? So when it's not a one-to-one ratio, there's an interesting way that they sort of, an interesting kind of geometry. It has to be kind of three-dimensional, but still it's sort of that alternating structure.